This is the lesson video for 5.2 Day 1. The topics in all of 5.2 are listed here, and you can see the ones that we're going to work on today are increasing and decreasing functions. We're going to tie that to our extrema work from 5.1, and then antiderivatives, which are a way of moving the opposite direction of what we've been doing with derivatives. So some video lesson reminders. You should be taking notes. You should be using the pause button to stop and think about things, catch up on notes, try something yourself first, and then go see. And you should definitely be going back if there's concepts or ideas you need to hear a second or third time in order to feel like you've got the big idea. So we need to start connecting our extrema to some things that we can do beyond what our candidates test let us find on closed intervals. We need to be able to have a way in calculus of finding extrema. And that means not from graphs, from the function, with techniques that we can defend instead of saying it looked like or I used a graph. So some things that we want to make some connections to then, and I have a graph to make these connections, is we see that there's a local max on the graph at x equals a. We want to think about what we actually know that would help us connect that. And one of the reasons we would have even looked at it in the first place is that f prime at a is 0. So that's what made it a candidate in the first place. But then there's two different things that we want to talk about. One is the way we would have described it in algebra, and then one is the way that we would approach that in calculus. What we do know at point A is that just before we get to x equals a, that function was increasing. So f is increasing immediately before it. And when I say immediately, so that we're not talking about a different portion of the graph, before x equals a, but then it's decreasing after it, which is how we know we got to a maximum. And that would be an Algebra 1 explanation of why that's a maximum. Now we want to talk about what calculus would say about that. And calculus wouldn't talk about f, it would talk about the derivative. And we would note that because the slope is positive before we get to x equals a, and the slope of f is negative afterwards. So our calculus reason would be that it's a maximum because f prime changes from positive values, not from increasing, to negative values at x equals a. And now we're talking about what the rate of change is. The rate of change was positive, and then it became negative, so therefore we have a maximum. So let's try it on the next one. We do not have an extreme value at x equals b. So algebra would have said, well, f of x is decreasing both before and after that ordered pair, so it can't be an extrema. And that would be a good Algebra 1 explanation. So now we're looking to see what calculus would say about that, and calculus instead would say f prime, the derivative representing the slopes, is negative on both sides of x equals b. Therefore, with no change in my derivative from negative to positive or positive to negative, the graph isn't reaching an extreme value. That's one of those points of inflections because it doesn't change sign would be another way to say that in calculus. So pause the video for just a second, see if you can come up with a way for how we might explain that C is a local minimum both in algebra and in calculus. What you want to be sure that you included is very specific things about f or f prime and at what locations. So we can't just say f prime changes. We can't just say because it changes. We need to be specific about what we're talking about. So going along with this is this corollary. And again, you can pause the video and write down the corollary about increasing and decreasing functions. And these are things we actually know, but they're talking about in calculus terms now. If our derivative's positive at every point along an interval, then from endpoint to endpoint, we consider that function to be increasing between those two values. Notice that the definition for what it's increasing on does include the endpoints. So then if the derivative is 0 at all the points in between the endpoints, then we'd say the function is decreasing over that whole interval from endpoint to endpoint. So what this is going to tell us is that we can use the derivative to decide how the function is changing, and how the function changes tells us about its extrema. So if it's a continuous function and the derivative's positive over an interval, then f is increasing over that whole interval. If it's negative, the derivative, over the entire interval, then f is decreasing over that whole interval. If we change from a positive to a negative, or a negative to a positive derivative, then we have an extreme point. So if I change from a positive derivative to a negative derivative, I'm going to have a maximum. If I change from a negative derivative interval to a positive derivative interval, then I'm going to have a minimum. This is how we're going to be able to identify local extrema instead of just the max and the min, and how we're going to be able to handle intervals that aren't closed. So we want to do similar to what we've been doing with our analytical methods, but this time we want to try to find all the local extrema and intervals where this function's increasing or decreasing. So I've given you both the function, and to take less time, I've given you the derivative. It's a derivative you yourself could find, and in homework you'll need to. We do want to look first to see if this domain has any restrictions. Same as we've been doing all along, we need to know if there's any endpoints. So the only thing that would cause us to have a problem here is if the denominator of our function were 0, and x squared plus 4 can't be 0. And if you don't believe me, do a quick check and see that to do that, x squared would have to be negative 4. So it is not possible. In other words, our domain is unrestricted. All reals. So then to look for extrema, we don't have any endpoints. There won't be any. So now we have to check for our critical points. And our critical points, again, are going to involve taking our derivative and finding out where f prime is 0 and f prime does not exist. So pause the video and find those, and then we'll come back to see what we do from there. To answer all the parts of what they want to know, both the local extrema and the intervals where the function's increasing and decreasing, we need to have a way of organizing all the information that we know about this function and about its derivative. So we often make what's called a sign chart. You can see my number line representing the entire domain of this function being all reals, and then representing those two critical points that I found. So what I want to do is see what happens on the intervals in between those. So from negative infinity to negative 2, from negative 2 to 2, and then 2 to infinity. And on those three intervals, if I can tell what the graph is doing, then I can identify extrema. So f prime, I have the function up above, so what I need to do is pick a value in each interval and see what happens to f prime. I don't need to see what value you actually pick, but just for this video, I'm going to show you what I'm using. F prime at 0 comes up negative. And I don't need to know negative what, I just need to know that it's negative and without a calculator. So when I'm evaluating that, I get a negative value in there. If the function's derivative is negative for that entire interval, that means that f is decreasing over that entire interval. So notice I've got this labeled, what f is doing and what f prime is. Then I want to check something in the other intervals. So I could check f prime at negative 3, I could check f prime at 5, just something in each of the other intervals, and both of those come up positive values. And again, don't need to know what, just need to know what their derivative values are. There won't be any other changes in derivative because we've already identified all the places the derivative is 0 or undefined. So everywhere else it has to be part of these intervals. So if my derivative is positive, that means that the function itself is increasing on that interval and on this interval. This information will tell us the answers to both A and B. So my local extrema, I happen to know the function increases until negative 2 and decreases afterwards. So that means that at negative 2, so negative 2 itself isn't our maximum or minimum, but it occurs at negative 2, we have a local max. They didn't ask us to find the absolutes, so all I need to realize is that it's a maximum of some kind. Our locals also include our absolutes. And then when we look at positive 2, we again have a sign change on our derivative. The function's graph went from decreasing to increasing, so therefore we have a local min at 2. Because the graph went from decreasing to increasing. So if you need that visual. Then the other thing it asked us for, part B, was the intervals of increase and decrease. Intervals of increase and decrease, if you look back at the definition from that corollary, include the endpoints, unless of course they're infinities. So we're increasing from negative infinity up to and including -2. And this will seem strange at first with those closed intervals, and we'll explain why when we can get into more details. And then it's increasing again, including 2 up until infinity. So then the interval of decrease is again inclusive -2 to +2. People get into kind of a hard thinking thing saying, but you're saying it's both increasing and decreasing at those points where it's changing. Agreed, and that's a little bit hard, but we'll explain later why that needs to be based on the definition, what point that's serving for us. All right, total changing gears, although this will all come together, is we're going to do some antiderivatives. So antiderivatives basically are working backwards. They're saying if you have the derivative, what was a function that it could have come from? So the math definition's there in the brown box. You could pause, write that down, and then come back. The directions will usually be specific or give a lot of specific information. So if it says find all the possible functions, the thing is that multiple functions can have the same derivative. The derivative of x squared is 2x. The derivative of x squared plus 1 is 2x. The derivative of x squared minus 7 is 2x. So there is a whole family of functions that have the same derivative, because adding a constant to the end of a function will not show up in its derivative because that constant's derivative would be 0. So when they tell us in this first example that the derivative of a function is x cubed, I know at least a little bit about what the original f of x had to have looked like. It had to have come from an x to the 4th function, because that's how derivatives work with a power that's numeric. But there had to have been a number sitting out in front, because otherwise my derivative would have had a 4 in it, and you notice there isn't, there's a 1. So the product of this 4 and this number sitting here had to have been 1. So in other words, there had to have been a 1/4 here so that when the derivative was taken, the coefficient became a 1. Here's what I don't know though, is if there was some constant added to the end of my original function. Because again, that could have been lots of different functions otherwise. So when they want all possible functions, I'm going to add that constant to the end because that says, oh, there could have been any different constant you wanted at the end of this function, and its derivative still would have been 1x cubed. So pause the video, try it with cosine of x and see what you come up with. So if you pause the video, hopefully you recognize that cosine is sine's derivative, but then to list every single function that it could have been, there could have been any constant added at the end, so you're giving the generic constant. The next example, they mention acceleration. Well, this is where we're actually going to get some application of this antiderivative. If acceleration is 3, that means velocity's derivative function is 3. So therefore, if I work backwards and take the antiderivative, I know that velocity was 3 times the time, and then there could have been any constant added to that. So I have a generic velocity, meaning I've got my generic or general antiderivative there because I don't have enough information to know if there was a specific constant to that problem. So now we'll do one where there should be a specific constant. So start by pausing the video and first just find the general antiderivative for this function. So your general antiderivative would be x to the 4th plus a constant. Then we have to take that specific information they gave us. They said the curve f of x, though, has to contain the ordered pair 2, 19. So when x is 2, f of x has to be 19. Taking that information, then I can find the specific f of x by saying, okay, 19 needs to be the output when, when 2 to the 4th adds a constant. So 2 to the 4th is 16. So the missing constant here is 3. So the specific f of x from the information that they gave me was x to the 4th plus 3. Now we're going to put that into a more word problem context or a situation problem. And they give us some information about on Earth the acceleration due to gravity is 9.8 meters per second per second. Knowing that, they tell us a dropped cell phone took 3 seconds to fall, and they would like to know its speed and how far it fell. So they've given us an acceleration function, and they've told us that acceleration as it hits the ground, 9.8. We're not doing negative 9.8 because we're talking about the distance it fell, and distance is never negative. But they're asking us about the speed or rate when it hit the floor, so I'm interested in things revolving around velocity. And how far it fell, well, that's related to position or displacement. So I need to be able to think through all three of these. So first, let's start with a generic antiderivative for velocity. So for acceleration. So the velocity must have been 9.8 t and then plus some sort of constant. We need a specific constant here. And we do have a little bit more information. We do know that at time 0, before the phone fell, it would not have had a velocity to the left or to the right. Its velocity would have been 0. So taking that information, I can find a specific velocity, constant anyway. So my constant is 0 here. I don't want to assume that. I want to be able to demonstrate why that's true. So therefore, my velocity function is 9.8 times the amount of time. So I can answer that first question, the dropped cell phone, what was its speed as it hit the floor? So it hit the floor at time 3 seconds. So its velocity at 3 seconds, 9.8 times 3, and therefore its velocity is going to be 29.4 meters per second. Then they want to know how far it fell. Well, to find out how far it fell, I'm going to need to know its position at time 3, where was it, and then its position at time 0, and do a displacement to figure out the amount of distance it traveled in between those two times. So I need a position function. So position, if I take its derivative as velocity, so velocity's antiderivative is going to be my position function. So I need to think about whose derivative was 9.8 t. So it definitely came from a t squared function. And then the 9.8 must have come from 4.9 times 2. Got to say plus a constant to be specific, or to be general at the moment. And then I do also know that at time 0, the distance that this had fallen, or its position, was 0 feet. So again, I can plug those two values back in to get that specific s of t having a constant, in this case, of 0. Do not assume those are always 0. Make sure you have evidence to know that. So therefore, I can now find s of 3. I know s of 0 is 0. And therefore, if I go find the position at 3, it's 44.1. Take away 0 meters from where it was when it started. So the total distance this cell phone fell is 44.1 meters. Your assignment then comes out of 5-2 day 1. And you can see the numbers, and I will slowly scan this. So if you want to pause the video at places and use it to do the homework from this instead, that you could.